So we've been covering vapor power cycles. We started this chapter by covering review of the Carnot vapor power cycle, and then we went into the simple ideal Rankine cycle, talked about improving the efficiency by superheating, by reheating, and then we talked about regeneration, especially a open Feedwater heater. And today we'll pick up with a closed Feedwater heater. We'll review how to handle non-isentropic pump, non-isentropic turbine, and then we will finish by talking some general considerations and some other topics associated with vapor power cycles. Let's start off with the clicker question. All right. And I don't know. Yeah, let's just start off. So for an internally reversible flow through the pump work can be approximated as the pressure in times the change in the specific volume, PdV. True or false? Well, look at that. 50-50, huh? So 50% are correct and 50% are incorrect. So why is this false? It's V dP. So it's V in times pressure out minus pressure in. This is one of those cases where the units will both be correct. So the units don't really tell you if you have an error, but they don't confirm that you have the right answer either. So that was how you fix it, hence the original statement was false. So we improve the efficiency by an open Feedwater heater. That's what we covered last time. So we take some fraction of the flow and divert it after the first turbine. And Y would be something like the mass flow rate that comes down in this pipe to feed the open Feedwater heater divided by the mass flow rate that went into the first turbine. So some percent feeds the open Feedwater heater, and the rest of it continues on in the cycle. Either it goes back for reheat or directly into the second turbine stage. Most probably goes into reheat. True? We spent some time trying to show the states on a TS diagram, a temperature entropy diagram. Often we have three pressures, don't we? We have a very high pressure. I've been running with some numbers like, the steam generator is operating at 8 MPa, that pass through the steam generator and into the first turbine. But after the first turbine, there's a pressure drop. Maybe this drops down to 1 MPa. And then it drops down after the second turbine into the condenser of 20 kilopascal. True? So when you're confronted with solving a problem like this, the strategy is make a table of all your properties, fill in the column for the pressures. Often you can work out the pressures at all the states. Then start with the temperatures. Some of them are typically specified, some are calculatable. When you go across a pump or across a turbine, you may be given the isentropic efficiency of that turbine, or you may just know, it's a 100% isentropic efficiency or an ideal Rankine cycle with the turbine then is isentropic. So you may know S. You may know the relationship S, T, or P. Okay. If you grab off 8 MPa, here's the line constant pressure of 8 MPa. Goes like that. And then if you also get a line of 1 MPa, here's the 1 megapascal pressure on a temperature entropy diagram. And then the line of about 20 kilopascal would be right here. True? Okay. And a lot of times when it comes to superheated, out of that steam generator at state 1, maybe it's at maximum temperature 450-ish degrees, and then that sort of sets where state 1 is, isn't it? That temperature, high pressure. Pass it through that turbine. At the best you can do, straight down. Actuality is going to be kicked over. There's going to be some higher entropy going out of that insulated turbine because of irreversibilities. And this, so you would walk around this property diagram. Okay? Does everybody feel comfortable they can walk around a TS diagram, put all the states on for a cycle? Here's some questions. On this temperature entropy diagram, where is the state? And let's do this. I'll kind of show an area, this area up in here, this area over in here, this area over in here, or this area over in here. We'll call this area A, B, area C, or area D. So where is state 2? Is it in the vicinity of location A, B, C, or D? You currently have 30 seconds. Okay, let's take a look at the responses. And most said C, which is correct. So what it is after that first turbine, you go from that high pressure to the intermediate pressure. I threw out 1 megapascal. It's not the condenser pressure of 20 kilopascal, not the boiler original highest pressure 8, but around 1. And when you pass it through, you're going to come straight down, and somewhere in this vicinity, typically along 1 megapascal line, is state 2. True? All right. Let's do this. Let's play the game again. And let's say, where is state, I don't know. Let's say, where is state 3? State 3. Where is state 3 on this diagram? In the vicinity of A, in the vicinity of B, in the vicinity of C, or in the vicinity of D? You know what? I should put E as none of the above. I'm sorry about that. Is none. I just noticed D is labeled as none, but I gave you a region for D. All right, let's take a look at the results here. Oh, I messed you up, huh? You were waiting to switch around. So most have selected this region, so it's close to B. Let's go ahead and get rid of this so I can see. What you're doing is you're going back at that 1 MPa and you're going back for reheat, aren't you? So now it's been reheated. It's very high temperature again. Typically it goes back to roughly the same temperature as 1, maybe a little bit lower. So we like to throw out something in the vicinity of 450 degrees C coming out of that after reheat. And you're at 1 MPa, somewhere maybe up in this vicinity. Okay? So that was the correct answer for state 3 is in the vicinity of B. Okay, let's do this one. State 6. State 6. Let's go ahead and start it. State 6 is after that first pump. All right, let's go ahead and see where we're at for this result. And so most of us said state 6 is in the vicinity of D, which is correct. Let's go ahead and look at this. We know that coming in to state pump at state 5 is saturated liquid at the 20 kilopascal, the very low pressure. So state 5 is right there. I don't know if I can draw it in a different color to emphasize. Isn't that where state 5 is? You put it through a pump. It boosts the pressure. And we've talked about that there's very minimal temperature increase, but the pump should be isentropic. If it's slightly irreversible, the S will go up a little bit, but 6 will be right on top of 5, essentially. Right there is 6. Maybe a degree C higher at the same entropy. So looks like D was the best answer, right? And that's what we selected. Should we do one more? Yes, sir.
Well, I'll ask after the next question.
Okay. All right. Let's do state 7. This is typically the hardest for people to figure out. State 7. That's what comes out of that open Feedwater heater. All right, let's see. Maybe this will get a lot. Oh, that's pretty good. Isn't it A?
Yeah.
It's A. Now, why is it A? Okay, think about this. We're about ready to go into the pump. If you're about ready to go into a pump, what is the best state of the fluid going into the pump? Saturated liquid. If it's condensed liquid, that's okay, but it's not maximally efficient. So it's saturated liquid is what we like to bring into the pump. So it has to be along that line in that vicinity, starting from this point at the top. I forgot the name of that point in the top. The critical point all along this side of the dome. True? That's where it's going to be. On that left side, all of these are saturated liquids. Now, what pressure is it? Is it that high pressure? No, the pump is going to boost it back up to something like 8 MPa. So, but it's not at 20 kilopascal. It already went through one pump, so it's at that intermediate pressure. State 7 has the same pressure as state 6, has the same pressure as state 2, which has the same pressure as state 3. True or false? Is that true, what I just said? Do all 4 of those states have the same pressure? Is the pressure at 6 the same as 7, the same as 2, the same as 3? Well, there's no pump between 2 and 3, is there? It just goes to a heat exchanger called reheat. So 2 and 3 have the same pressure. We have an ideal system that if you're going just for the heat exchange, like in the condenser, the heat exchange, and the first pass through the steam generator or the reheat, those don't have pressure gains or pressure drops. They're essentially the same pressure.
But wouldn't 2 or 3 be less than 2 because you're losing part of the pressure, a percentage of the pressure going to from 2, 3 and to 7?
That's correct. We do have some frictional losses in reality. Anytime fluid flows through through a pipe of any length, there's a pressure drop. Anytime it flows through the heat exchanger, the coils of the heat exchanger, there's a pressure loss. But in this class, we don't model that pressure loss. It's the engineers try to minimize that pressure loss by giving it sufficient diameter in the pipe and sufficient area to go through that heat exchanger. But you're absolutely right. In reality, there's a small pressure loss. Anytime, any length of pipe, there's a pressure loss. But hopefully it's small compared to the pressure gains for the pumps and the pressure drops across the turbines. Those are the two devices where we have our big pressure changes.
Are you assuming that pump 1 and pump 2 have the same pressure?
Nope. Nope. They're both saturated liquids coming in. Saturated liquids coming in. But this one may take it from 20 kilopascal to 1 megapascal. That's about a 1 megapascal gain. And pump 2 may take it from about 1 megapascal to an 8 megapascal. That's about a 7 megapascal gain. So pump 2 is really big.
So how are you saying that 7 and 6 are equivalent to 2 and 3? Because it's before pump 2.
Yeah, you just said 6 was 20.
You're saying
No, 6 has the same pressure as 7, as the same pressure as 2, as the same pressure as 3. The same pressure. Did I misspeak?
I was assuming that you were saying that 6, 7, 2, and 3 were all the same pressures.
They are. Yeah. So at 6, you boosted it to 1 megapascal, and this is 1 megapascal. The pump takes from 7 to 8. Now it boosts it up. So it's 1 megapascal in, out, 2 ins, 1 out, all at that open feed water heater. Open feed water heater has the same pressure.
How is it that in one pump, in the second pump, you have such a huge pressure boost compared to the first pump?
Well, those are the numbers I threw out. You could go from 20 to 2 megapascal, and then from 2 to 8. You could go from 40 kilopascal to 4 megapascal, and then 4 megapascal to. But what happens is if you go too high a pressure, let's say it falls from 8 to 4 megapascal, that first turbine is not going to look so good. It's just going to go like that. I mean, come on, we want to get it down. So that first turbine has a large pressure drop across it. If you're bringing it in, state 1 is right here, and then you want to take it slightly into the dome. 1 megapascal looks good. If I take it down to 500 kilopascal, well, maybe I'm getting the quality isn't as high as I would like it at the exit of that first turbine. Okay. Did that help? Any other questions? So those, yes, sir.
Okay. That was actually my question, where state 7 was at.
Right. Oh, did I not show where state 7 is? It's at that 1 megapascal, come across, and it's saturated liquid. Okay, well, maybe I should have drawn this part A to be a little lower, but it was closer to A than anything, right?
Okay.
Most people, it was on the edge. I drew it quickly. But that's where state 7 is at. Oh, where's state 8? Oh, that'll be a redeeming question. Let's play one more of these games. State 8. Where is state 8? Close to A, close to B, close to C, or close to D? State 8. All right, so let's go ahead and see what we have. Most people said A, and they're correct. True? Now, why is it A? Well, let me come in here, and I have to say that it's at the 8 megapascal line. It's at megapascal line, but it's compressed liquid. And just like 6 was a little above 5, that second pump, number 2, took 7, which was at state 1 megapascal saturated liquid, and put out state 8 right there. So that's where state 8 is. That makes sense? So
It has 8 megapascal pressure.
it has 8 megapascal pressure. That's right. And so these lines, like the 50 megapascal, 100 megapascal, all that, they're all crammed in here. They're all crammed in there. They're definitely lines, and I blew them up before and zoomed in to show you that, oh yeah, it's at a higher pressure. Same
temperature as SS7?
It's about a degree higher. About a degree higher. Maybe half a degree, maybe 1.5 degrees C, somewhere in that vicinity. I usually just say 1 degree C higher. On this scale, here's 200. Where's 201? Yeah, it's too hard to. It's the 1 degree C higher is almost imperceptible.
Would state 4 and state 5 be saturated liquid?
State 4, right here. All right, let's continue to play this game. State 4. Where is state 4 coming out of that second turbine? And you know what? Maybe I should stop this for a minute. Let me give you more time. I'm going to give you more time. And what I'm going to do is I'm going to rearrange all of my locations. All right? I'm going to say, right in here is A, right in here is B, right in here is C, and right in here is D. Those are my new areas. You have a minute to do it. So those are my new areas. Okay? Is it around A? Is it around B, C, or D for state 4? This is what I like to do sometimes too, is we'll do this. We'll show the results, which you can do. And students, you can now even change your results. You can watch the B's go up and the C's go down and the A's go up and the A's go down, right? You're just gonna see how intelligent students are. This looks like the primaries. It's all over by New Hampshire and Iowa. It's all over. Everybody's on the bandwagon. Go ahead and play with it. See what you can do. Can you make it go to B and E, then go back again?
State 4 is just after turbine 1, right?
State 4, I covered it up. It's right after the second turbine. Right after the second turbine. Now I'd encourage you with 19 seconds left to rush to the correct answer. And I think we'll go ahead and stop. Look at that. We have 100% correct. I'm an educator. Somebody said, why don't you just do this, the lecture right before the exam. Just tell us what's on the exam. Educator. I'm an educator. If you do that, right? All right. So that was a lot of fun. That's correct. State 4 would be at that 20 kilopascal. It's the lowest pressure, right? And it's somewhere high quality. You want it high quality region. You don't want it low quality. Okay. Now the next thing we can do is we can do what we call closed feedwater heater. A closed feedwater heater allows the pressure for the fluid that's warm and giving up some heat to be different than the pressure of the fluid that's going through and receiving the heat. I'm trying to color code red for the hotter fluid, blue for the cooler fluid. And so there's a heat exchange from the fluid that's going from state 2, this is the inlet state 2 right up here, to the outlet state 8. Think about the enthalpy at 2 and the enthalpy of the fluid at 8. Which enthalpy is greater? Non-clicker, just call it out. Which enthalpy is higher? is higher enthalpy. No, it's the fluid that comes in and is transferring heat out of it. The heat is transferred in this heat exchanger out of the fluid that's going from 2 to 8. There's heat transfer out of that fluid. And where is that heat transfer going? It's going into the cooler fluid. All right? So which enthalpy is greater? 2. Enthalpy 2. Okay? Then likewise, I look at the enthalpy at 6 and the enthalpy at 7. Which enthalpy is higher? 7's higher. 7 is higher enthalpy than 6. Okay? And so this was the direction of the transfer of thermal energy. Typically I say it's heat transfer, which is inside that heat exchanger. It's going from one fluid stream into the other fluid stream. Okay, now this steam right in here may be some very high quality pressure steam, high quality. Maybe the quality at 2 was, I don't know, 97%. True? So what you can do is if it's coming out at the same pressure, the pressure at 8 equal to the pressure at 2, there's no pressure change in that fluid stream. There's no pump or turbine, so we're going to neglect the pressure change. Yes, in the real system there's a small pressure drop, but here we're going to neglect that pressure change. What is the condition of the fluid coming out at 8? That would make sense. What is the condition of the fluid comes out at 8? It's going to come out the same pressure that 2 was at, and it's going to have transferred a lot of energy, a lot of heat out of it. A low quality. What's the lowest quality you can get? Saturated liquid. So often we want that fluid to come out at saturated liquid. So the energy that it gave up was the quality at 2 times HFG per kilogram that went through it. What's HFG? The heat of vaporization. Well, is that the same as the heat of condensation, so to speak? I know we say the heat of vaporization, thinking I've got to put in so many kilojoules per kilogram to change phase, to make it vaporize, to boil it, to go from saturated liquid to saturated vapor. Let's say it comes in at, I don't know, some 97%. Well, 3% is already condensed, and I need now condense the 97%. And so that occurring at constant pressure allows us to calculate how much heat comes out of that fluid stream. Where does it go? Into the other fluid stream. True? Okay. So we already talked that H7 is greater than H6. We already spoke that H8 is less than H2. What is H8 actually? H8, will that be H of F at that pressure? Sure will be. Okay. All right. So we got an idea of what's happening in this closed Feedwater heater. Why do they call it a closed instead of an open? They don't mix. There's a wall, some high conductivity solid material that has minimum resistance to heat transfer. That's why it's high thermal conductivity. But it separates the two fluid streams so they don't mix. Okay. Now, let me do this. What is the pressure at 8 compared to the pressure at 1? The pressure at, not 8, the pressure at 7. What's the pressure at 7 compared to the pressure at 1? Is it greater, equal, or less? Okay, clicker question. A, B, C. Look at the pressure at 7 and compare it to the pressure at 1. Where is state 1? State 1 is right here. Where is state 7? Right there. So is it pressure at 7 greater than the pressure at 1, equal to the pressure at 1, or less than the pressure at 1? Pardon? Oh, show the polling. Yeah, that's only in special cases. Is it your birthday today? If it's your birthday, then we can do it. Oh, it's tomorrow? Somebody has a birthday tomorrow. All right. Well, congratulations to the 51%. It's the same pressure. Let me ask you, is there a turbine between 7 and 1?
No.
Is there a pump between 7 and 1? It's a heat exchanger, and we neglect or we just ignore. We know that, yes, there's real pressure drops and real pipes, but compared to what the pump increases the pressure and the turbine decreases the pressure across those devices, there's negligible pressure change between 7 and 1. Correct answer is B. True? True. Okay. So now the question is what happens is you almost always have to specify the temperature at 7. It has to be like given in the problem statement. That's a little different than most. A lot of times we say, oh, it needs to be saturated liquid. That's the best. Well, I'm telling you, it would be too high a temperature at 7 to be saturated liquid at that high pressure. Okay? So often T7 is given, and T7 is below the saturation temperature at the pressure of 7, significantly below it. But what T7 is close to T8, the temperature that comes out. This is a tough question. I don't think I'll get 100% correct, but I'm going to ask it anyway. So I want you to compare the temperature 7. Do you think it would be just, it's going to be greater than the temperature at 8? Going to be precisely the same as the temperature at 8, or a little bit less than? So a little bit greater, precisely the same as, or a little bit less than the temperature at 8. Answer A, B, or C. This is a probably unfair question. Sorry if you get it wrong, but I want you to think. Everybody's in. All right. Well, that's pretty good. The temperature at 8 is greater than the temperature at 7. Temperature at 7 is less than the temperature at 8. Now let me try and explain. I know that was a tough question, but here, let me ask a simpler question to help redeem you. This will help redeem you, okay? I want to compare the temperature at 2 and the temperature at 8. All right? Where's state 2? Right after that first turbine, it's coming into the closed Feedwater heater. Is it going to be greater than, equal to, or less? The temperature at 2 compared to the temperature at 8. I'll start that right now. Now you have 30 seconds. Maybe the Socratic method isn't so good after all. What's the Socratic method? You just keep asking questions. You don't tell somebody the correct answer. You lead them to the correct answer by asking them questions. When they don't get it, you break it down to smaller questions in steps. And it can be very laborious and labor-intensive to do that, but it does work. It's just, it can be a lot of times it's like, in the military, do they employ the Socratic method? Does the general employ the Socratic method? I would like to continue to ask you questions until you come along with my line of thought and reasoning. So it don't, so anyway. Ouch, this one hurts.
H2 is more than H8.
H2 is greater than H8. P2 is equal to P8. It's saturated, high quality going in. It's saturated liquid going out. I thought that was the easier question. Talk about the pressure at 2 versus the pressure at 8. I know.
Is it the same thing as 7 and 8? It's kind of?
Okay, this B is the correct answer. And now we go and we will drop back. Maybe a diagram will help us. Here is a temperature entropy diagram. I know that I'm changing it up, but let's say that that was a 1 megapascal pressure line. True? I want to sketch it. Notice right there. And how am I sketching this line in the dome? It's a straight line. Does the temperature change at all? Nope. And if you remember, that was around 295 degrees C, the saturation temperature of steam at 1 megapascal. True? So it came in at state right around here for 2. That was diverted, and some of it was diverted down to that feedwater heater. And then what happened? It was heating up the other fluid. But as it was transferring heat out of that stream, that fluid stream from state 2 to state 8, the temperature of the fluid didn't change from state 2 to state 8, did it? It just condensed. This is one of those oxymorons. It just doesn't make sense to students, right? So we talked about the heat transfer that was going from the warm fluid to the cool fluid. True? That heat transfer is occurring while one of the fluid streams isn't changing temperature. The hot fluid is not changing temperature. It comes in at T2, goes out at T8, and T8 is equal to T2. It's condensing at constant pressure. Does the enthalpy change? Does the quality change? Yes. Pressure? No. Okay, let's go make our long list of properties. Pressure, temperature, let's go U, let's put X for quality, V, U, H, S. We should be able to talk about how each of these properties changes between state 2 and state 8. So the pressure at 8, the temperature at 8, the quality at 8, the specific volume at 8, the internal energy at 8, the enthalpy at 8, and the entropy at 8. All of these at 2 versus 8, 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 2 versus 8. True? I've kind of done it piecemeal, but let's do this now. What about the pressures? Is it equal? Greater? Less? Which one is it? Equal. How about the temperature? Equal. How about the quality? Which one is 2 greater? X2? 2 is greater, right? Let's skip the specific volume and we'll come back to it. Let's skip the internal energy. We will come back to it. Enthalpy. H2 is greater. 2 is greater. Entropy. We should be able to figure that one out. H2 or HS? 2 greater? S. Entropy. S. Here's a little help. What's on this axis right here? Right? So, which one's greater? 2. 2 is greater. All right. Now we can maybe drop back to internal energy. Greater, right? Greater. How about the specific volume? Take your hands like this and say, this is the volume 1 kilogram occupies. Does it go that way or does it go that way? Does it go down or expand? Which one? Look good? All right. So maybe we should do that and walk through the whole diagram and help get that relationship, because it's easy to mess something up, and as you're crunching numbers and you're solving problems, you should interrogate your results kind of as you go. True? And if you interrogate results as you go, you say, yeah, that looks reasonable. It's up, it's down, it's the same. And then, oops, no, what did I just do? Let me check my calculator. Try that number again. Okay? So, T7 versus T8. Well, you have to have the heat transfer from the hot fluid that's being pumped into the cold fluid, and the hot fluid's not changing temperature. So what do you think the cold fluid needs to be? I mean, the bottom line in heat transfer is let's do this. If I have something that's hot in communication with something that's cold, what is the direction of the heat transfer? From the hot to the cold, from the cold to the hot, or it could go both ways. It really depends on Monday, if it's Monday at noon, or Tuesday at lunchtime, something. It goes hot to cold, doesn't it?
Yes.
This is just a dumb heat exchanger. I have a hot fluid stream and a cold fluid stream. Got it? The cold is always lower than the constant temperature hot fluid stream. So, which one? T7 is going to be less than T8. I get back to that original question that I graded, which you had a higher percent correctness on than this one. I thought that one was harder. But, all right, this had the very low percent correct, didn't it, as a class? Yes, sir.
I was just confused. When I was reading the chapter, it just shows those states just above. That means like the book. That means T.
Well,
T2, like T2 in the book, it shows different numbers, but it being the superheated, just barely.
okay, let's go to this. Oops, I do have to go. I have to go back and reuse this diagram. And let's say we bring it out of the boiler at around 450 at 8 megapascal. So we're right about there. We talked about if you bring it down to just maybe 4 megapascal or 2 megapascal, you're in the superheated region. So let's get it down definitely into the two-phase region, and that's 1 megapascal will do it. All right, now we're there. That's state 2. Some of that 2 is diverted over and now comes out at state 8. Okay? Now, state 7 needs to be somewhere like right in here. Right in there. Now, can a textbook give you a problem where they show and they assume T7 is greater than T8? Sure. If they did that, the only way that would happen is if they stopped somehow and they brought out some superheated, then it condensed, then it went this way, and now there's a possibility that 7 is above 8, but I didn't portray that, and that's more rare. You don't. Did they have a problem like that?
Yeah, it was just almost all the diagrams and the examples are like that.
Let's take a look. I have the textbook in front of me. Which figure are you looking at? What page or something? Figure 811.
470.
Well, they have 6 below 7. Oh, I have the old book. 8, sorry. Which, But that one I just looked at, they have correct. I'm looking at another one, and 11 is below 12. That's correct. I think the textbook publisher would want to avoid putting the temperature of 7 greater than the temperature of 8. They just would want to avoid that. Now, can they do it? Yes, if temperature 2 is greater than 8. Should they ever show 7 above 2? No. The temperature 7, never above 2. Now, I've even made up exam problems years ago where I threw, I'm not thinking, I just threw in a temperature of 7 above both of them. You know what you can show then? That's an entropy destroying machine. This is a great machine, and it violates the second law. You can get it to violate the second law. It won't make sense. Or maybe it's not entropy that it destroyed. Maybe it was exergy that it produced. Or hold it. It messed up the second law. And I can't remember. This has been a number of years ago that I did that.
Both ways are right.
Both ways are right? Yeah.
Entropy construction and entropy destruction.
Right. So it destroyed entropy and generated exergy, which was terrible. All right. Now let's talk about this device right here, which I forgot to emphasize. It's called the steam trap. All right. Well, everybody think. What comes to your mind when you see a trap or the word trap? Right. Something, maybe a hole in the ground and the animal falls into it and stays and is trapped, right? Or something like that. I don't know what comes to your mind, but it's a trap, okay? What happens is you want this fluid right here to go condense. To condense. When it condenses under the influence of gravity, it'll collect at the bottom, and then you pull it off the bottom. But you don't want it to just have vapor flow. So it's like a little police officer that's directing traffic, and he says, back up, hold up, until there's a pile of cars behind you, until there's a pile of sufficient liquid condensate behind you, and then I'll let some of the liquid condensate go, and if there's 10 cars, right, they'll let 9 go, and the last car they'll say stop until there's another 10 cars piled up. Then they'll let 9 cars go, and the car wants to really go, nope, you stop. And that's what a steam trap is doing. It's holding it back. Now, to understand that steam trap, I really have to take a look at what's happening after the steam trap. At state 9 is after the steam trap, and where does it go? It just dumps into the condenser. All right, well, what do you think the pressure at state 9 is compared to the pressure at 4 compared to the pressure at 5? The pressure at 9 compared to 4 and 5? Equal. They have to be equal pressure. Okay, so what does that say about the pressure 9? Something like 20 kilopascal or some other number. I'm throwing around 20. I'm trying to stay consistent. That's a low pressure. Let's see, it was 1 megapascal over here. It's 20 kilopascal over there. What happened across this steam trap? There's a significant pressure drop. Okay? So that's what happens is there's a significant pressure drop. Now, these devices are used to hold back live steam. That's a word like live steam. It has some vapor phase to it. And they will let the liquid condensate through. Now, in real systems, not only do you condensate, you also have the possibility of having in there non-condensable gases. Where did they come from? Well, life is life, and when you get water out of the tap, there's some oxygen and some other dissolved gases in it. The fish love the oxygen. Other plants or whatever love the oxygen. Maybe plants don't, but things need it in the water, true? So when you get it out of the tap, there is gases in it. There's CO2, there's oxygen, whole pile. Well, they like to come out when it's warm water, steam. So they'll come out where it's low pressure, high temperature. Now you have gases separated from the liquids. Sometimes they'll go back in the solution. Sometimes you just get them out of the system. So you'll have non-condensables, and the engineers have to design it to get rid of it. So anyway, this is a device. It's a clunk of metal. That's unfortunate about mechanical engineering. Sometimes these very expensive, very highly engineered devices, you just look at it, it's a clunk of metal, right? You ever look at the engine just sitting on the floor? It's like, you got to feel an engine behind, in the seat of the car to really appreciate an engine. You look at it laying on the floor of a shop or something, it's like, like whoopee, right? It's a big clunk of metal. But this end is highly engineered, so let's take a look at how it would work. Now, this video out on YouTube is 31 minutes. It was produced in about 1984, something like that. It's old. But steam traps haven't changed that much.
Like a little extra pressure boost.
Float and thermostatic traps offer a combination of mechanical and thermostatic operation. A closed float is used to sense the density difference between a gas and a liquid. The float is attached to one end of a lever which pivots inside the trap. At the opposite end of this lever is a valve that is seated when the float is at rest. Condensate enters through the inlet near the top of the trap and raises the float, opening the valve. The condensate drains from the trap through the outlet near the bottom, leaving a condensate seal between the inlet and the valve. Above this seal, near the top of the trap, is a thermostatic bellows. The bellows responds to temperature change. When this space is filled with hot steam, the thermostatic valve is closed. Non-condensables, such as air, mix with the steam and cool the space near the top of the trap. When the bellows element cools sufficiently, the thermostatic valve will open and vent these gases into a passage leading to the trap discharge. At startup, the float is down, the float valve closed.
If you're really interested in steam traps, take a look.